Hi, my name is Professor Dr. Mehdi. I'm a professor right now in Hunan University of Arts and Science. I'm currently working as a senior consultant, total artificial heart transplant with the United Christian Hospital and Peking Union Medical University. I'm also a senior consultant for the RFIC, MMIC, and MCU chip designing, and also nanotechnology like for submillimeter, millimeter radio astronomy, terahertz circuit design in the clean room. And I'm being collaborate with the in Chile with the University de Antis with some professor working on terahertz devices. I'm also a CTO in observing robotics for biomedical devices and radio astronomy devices. And I'm also like patron in journal Journal of Medical Electronics and Mechanical Circuit Support just for journal publications, and also I'm a patron in the International Society of Medical Electronics and Mechanical Circuit Support. Okay, so today we're going to talk about the radio astronomy like ALMA, Atacama Large submillimeter millimeter terahertz array. So my topic, I'm going to talk about the background, about my background, and applying for the proposal for band 6 to study the jet structure of black hole. Currently the ALMA is like asking people to apply for this proposal. I'll talk about the terahertz advantages, the constraints, the applications. I'll talk about the terahertz sensor, frequency, telescope, telescopes and circuits, and there are type of telescope. I'm going to talk about the radio astronomy, interferometry, antennas, and the terahertz circuits, and why we need radio astronomy. I'll talk about the ALMA and black holes. And moreover, I'm going to talk about Einstein theory of relativity, special relativity, space travel, near black hole, observatory evidence for black hole, gravitational waves, and observational evidence for black hole. I'll talk about the general theory of relativity. I'll show you some video. M87 interferometry video, black hole and general relativity. And lastly, we'll talk about the black hole, Sagittarius A star, how we do the image averaging and polarization. Here we go. So I used to work in Sweden in Chalmers Joint Lab of JPL, Jet Propulsion Laboratory, and Onsala Space Laboratory. My work was like making terahertz devices like coupler filter and hot electron bolometer SIS mixers for ALMA projects. So I'm more like hardware design. This is my research articles. Just show you currently like quadrature wave coupler with H-plane horn antenna for 2.5 terahertz, and on the right is talk about the Hampton SIS mixers. Okay, I work as a CTO in the Chinese Silicon Valley, and that company was Hamtong. It is the 7th largest company, and my main objective during my CTO is like making MCUs for smart cars, ASIC design, RFIC and MMIC, and also we can do nanotechnology for MEMS sensor design for specific applications. Okay, currently, right now I'm working with some doctors to make some artificial heart to be implanted in human, and I'm working with Chinese doctors in Peking Union Medical University, and also in Pakistan I'm working with Dr. Parvez Chaudhary, and you can see me this thing, and on the down you can see the structure. Like this is the heart structure, and this is like artificial heart. Then we can implant this thing here. Thank you. And this is my conference about total artificial heart, and I was in the presentation on total shot. Okay, so as we talk about in the background, so this is like some proposal like for VLB, like the ALMA wants like people apply for the proposal, and they want some people who can design band 6, especially the band 6. Why they need band 6? Because they want to see the jet properties of the black hole, and also using the band 6 to see the polarization, like to use the stroke 1 to detect the continuum morpho into jet region, polarimetric image like polarization, like we talk about the stroke 1, we will talk about this thing, understand the role of magnetic field around the black holes. So also they want to make this band 6 observation a proposal to make a target flux density like for the band 6, and this is all about the project, which was deadline 31st January. Okay, Terahertz advantages. So it is a strong interaction with matter. It has a strong interaction with matter. Significantly penetrate in some materials. Naturally occurring spectral signature. Natural frequency for femtosecond probing. Very high sensitivity for signal detector. Aperture advantage over millimeter, and it can do non-ionized radiation. It has low tolerance of optics, huge available band. It has very huge available band, untapped potential. And also terahertz constraint. There is some constraint in terahertz, like high material loss. Like we can have a high material loss in metal and dielectric. Poor atmospheric transmission because of the ozone layer blockage. So noise background limit, signal detection, there is a high noise, few natural resonance except in low pressure, poor contrast, huge spectral ratio, millimeter scale focus at best, large aperture, we need a very large aperture, and seriously guide medium dispersion, and there is a high dispersion losses, and it costs too much to making component. Okay, traditionally terahertz right now we use for the space science like astrophysics, Earth, to know about the Earth materials, to know about the planets, we know about the comets and asteroids, and also we can use this terahertz application in plasma diagnosis, in space, galaxy, and non-destructive evaluation, assorted niches. We can see about the gas spectroscopy in quantum physics. Okay, and this is what the picture is. Talk about the whole band, terahertz band, and atmospheric transmission. So here we can see this region, like here, from 1 millimeter to some 0.3 millimeter, kind of like this thing. There is a gap, atmospheric opaque, where we can use this region to make terahertz devices, and we can see about the galaxy and stars and about black holes and everything. So it is the best area which we can use this area, because the other area, if you can see, very high frequency microwave, millimeter wave, they have a high blockage, high attenuation, which block the radio frequency to go to the or other layer to see the skies and this thing. So that's why we use this region to make terahertz devices for the atmosphere. So here we're going to talk about like terahertz has some like it is the window 0.3 to 3 terahertz, and we can see it has gases in this, and they absorb electromagnetic radiation to most wavelength. And the visible light, as you can see from here, this is the visible region. Most radio wave and some infrared penetrate the atmosphere. They can penetrate the atmosphere through atmospheric window, wavelength region of high frequency. Lack of atmospheric window at other wavelength is a reason for atmospheric placing telescope in space. So here is like terahertz for outer space. We can use terahertz in other fields. Like here we can have a airborne platform where they can use terahertz devices using this thing. and we can use Earth orbit surrounding planetary sounds. We can use in space for terahertz devices. So this is like astrophysics driving terahertz sensors. So we can see here from this graph, this is spectrum of interstellar dust. The, the terahertz is useful for study stellar and galactic constitution and evolution, cosmology, dust and gas chemistry. So we can use terahertz devices to see about to study about stellar and galactic constitution, evolution, cosmology, dust and gas. And here we can see this is the optical image and this is the terahertz image, and this is the graph where we can see the atmosphere is covered with so many gases around him and dust, and then we can use terahertz device to see that thing more clear thing as compared to optical telescope. So here is we can see the galactical emission at terahertz frequency. So here we can see half the luminosity and 98% of the photon released since the Big Bang. They have a 98% release of photon since the Big Bang fall into the submillimeter and far IR region. So from the left graph here we can see the lambda from the x-axis, and then we can see the energy output versus the wavelength for the galaxies of ascending ages, showing advantages of terahertz detection for probing the early universe. So we can see the earlier universe using terahertz devices. Also on the right hand side we can see the Milky Way galaxy. So a spectrum of the Milky Way showing the luminosity output versus the length versus intensity versus wavelength, almost 50% of the power at terahertz frequency. So okay, terahertz telescope is pretty expensive. As we can see from Herschel Space Telescope was launched in May 2005 by a European satellite. After 24-year development, it cost us $1.5 billion. And literally hundreds of astronomers and engineers work around this to make this telescope. So major driven are cosmic dust. So to major driven to make this thing are the cosmic dust star formation, to see about the cosmic dust star formation, galactic evolution and cosmology. 90%, like I told you, photon we measure in the universe fall into the terahertz region. So it is very important we go for the terahertz devices. 11 astrophysicist missions with terahertz sensor have flown 697. So on the right side we can talk about the planetary remote sensing, also comet and asteroid like Earth sensing is very strong driven for passive and perhaps even active terahertz spectroscopy. So it can detect water, carbon, methanol, and many other gases using different frequencies. Only one terahertz planetary mission has launched to date, MIRO, into zone, but many more are in current and will be in future launch. Although space applications are niche, the funding level are constraints worldwide. Okay, this is like terahertz circuit. So here we can see this is like a antenna. This is like antenna here, and it has some SIS mixer or hot electron bolometer mixer, and with some IF amplifier. So normally the signals come from here, then it goes down convert with the cryogenic. This is cryogenic at a very low temperature superconductor, and then it go to the IF frequency to do signal processing of the images and using computer kind of thing. So this is like a computer simulation of this thing, and this is the practical image of this hot electron bolometer and some low pass filter around him, and this is how we can see how we can design this thing in the clean room for terahertz devices. So there are different type of telescopes, like we have optical telescope sizes, image and detector, high resolution astronomy, and we will talk about the radio astronomy in ferrometry and the ALMA array. This is our main topic right now. So radio astronomy, like radio telescope, similar to optical, is similar to optical reflection telescope. Primary focus less sensitive to imperfection due to longer wavelength and can be made very large. It can make very large size as we can see from here. Radio astronomy, largest radio telescope is the 300-meter, as you can see here, dish at Erbic. So this one is the largest one, uh, the telescope where we can see 300-meter and at the Arecibo. And the radio astronomy, longer wavelength means poor angular resolution. If you have a longer wavelength, we will have a poor angular resolution. Advantage of radio astronomy we can observe for 24 hours. And also cloud, rain and snow don't interfere. It don't interfere with this thing. And observation at an entirely different frequency. Get totally different information. With different frequency we get the different information because every frequency will tell about the different gases and dust. What is this thing? We will talk about this thing in the next slide. So interferometry is like a combination of information from several widely spread radio telescopes, and it came from this single dish. The resolution will be that of dish whose diameter is equal to the largest separation between the dishes. So how can we see the resolution? So there is a formula of resolution is equal to lambda by d. So if we have like lambda by d, then we can know this thing. If we have a very big dish, we can have a very high resolution if we want to see black hole because it's very small. But the good thing, we can make a distance between two telescopes, then we lambda by d become a distance, the difference distance, and that make the resolution much better and a more intelligent way than making a one big dish. So interferometry involving combined signal from two receivers. The amount of interference will depend on the direction of the signal. So like it will have maybe a destructive, that means it can become combined and make it zero, or maybe constructive, that means add together and make it bigger signal. Depends on the signal how it reach here. With some phase, with no phase difference, that means destructive. So ALMA interferometry, if you can see from here, it is like it has so many dishes, then it combined with some phase, and then it do the increased signal and mark record. So this is the image for the interferometry. Can get radio images whose resolution is close to optical. And interferometry can also be done with visible light, but it's much more difficult due to shorter wavelength. So this is like one more interferometry, which is ALMA. The ALMA array is a set of six radio antenna located in Chile, which detect radiation with wavelength between 0.3 to 10 millimeter. The antenna are mobile, allowing excellent resolution. So here we have the ALMA array. You can see the image shows a protoplanetary disk surrounded the star HL Tora. So this is the image taken by the ALMA array. Here we can see show the prototype disk. Here we can see a disk-like structure surrounded by the star HL. This is star HL Tori. So here we can see very good image using the ALMA interferometry technique. So normally this is like a radio astronomy system. So here you can see radio astronomy. This is the image which we want to take. Then it comes to here. This signal comes here. Then we get has some kind of this source, and we have some Earth atmosphere, antenna collecting this signal, and then we have a front end cryogenic receivers, and this is the back end amplify and transport signal, and then we do the spectrum reconstruction, and then we can see this signal visualization. This is more like radio astronomy system, how normally it works here. So this is like a structural way how it look like the radio astronomy system. This is for the if we have a frequency less than 100 gigahertz, then normally we should have a low noise amplifier before the antenna. Then we have some gain amplifier to increase the gain. But as we go for the terahertz, then we have to use the mixer because we don't have the devices that can work at a very, very high frequency. Then we use a physics mixer like hot electron bolometer SIS mixer. And then we can use these mixer down-convert, and then we can do the low noise amplifier, and then we do the signal processing of that image. And here is one example here, which I show the Whitestone bridge. Here, this is the hot electron bolometer structure. We keep the two resistance here constant. Here is the resistance, and this is the metal resistance, metal kind of this thing. So we put the HB, some photons come here, then it will change the resistance. More energy come here, it become heat, and the resistance also get higher, and then we get some current here. So more we photon, more we increase the current, and then that current will go to the signal processing for further analysis. This is like a simple circuit analysis of this SIS mixer, or we can say hot electron bolometer mixer. So why we need radio astronomy? Here we can see this is the galaxy here. Here we can see so many dust here, which we cannot see from optical way. As we can right side, you can see these are the optical telescope, which make it far much difficult for us to see the high because it's covered with it. Because when star is very hot, like so it emits so many hydrogen and so many dust and gases, so it's difficult for us to see this thing. So then we use radio astronomy to make it more clear. So it's kind of like stunning images taken by optical instruments like Hubble's telescope are famous worldwide, but there are many details they cannot see. So the radio astronomy revealed part of the invisible sky by detecting radio waves emitted by the wave range astronomy object phenomena. The radio telescope provided a totally different view of our universe. So why we need radio astronomy? Here we can see, so what is the use? It can use for the cold universe we want, not hot. So we can see the material, how much they are, what is made of, how it's moving, its temperature and chemistry. So this is, we can use the terahertz frequency and we can figure out. And on the right side you can see we use different frequencies, like these are the different frequencies, and we can see which material is this one. With using this material in these frequencies we can find the material properties. If we're using radio astronomy, then we can know this is hydrogen or this is silicon oxide, whatever, oxygen or whatever, dust. We can use different frequency and we can find the material. And here we can see here's so many, the red color is more like hydrogen emitted by the star, and we cannot see inside. And this is like nebula. Here we can see this is kind of like a nebula of Orion, and this hydrogen gets released by the star and new star gases. So if we want to zoom this area, here we can see this make with the optical image, and this is like an infrared image. Then we can go for the radio study of cold gases. We see the gases and dust, and we can this is the EFC era, 10 years later away from the disk. This is the disk round, and this is the small star. So we can see this is the Burick disk comet collision, and we can see this thing very clearly using radio astronomy. Okay, this is like ALMA video here.
Welcome to the video. Today we're talking about the Atacama Large Millimeter/Submillimeter Array, ALMA, located in one of the highest and driest places on Earth, the Atacama Desert of northern Chile. ALMA's strategic location at an elevation of 5,000 meters, 16,000 feet on the Chajnantor Plateau reduces atmospheric interference, providing optimal conditions for astronomical observations. ALMA is designed to explore the universe in the millimeter and submillimeter wavelengths, which sit between infrared light and radio waves in the electromagnetic spectrum. This range is vital for studying the cold universe, including molecular clouds and the early universe. ALMA has the unique ability to detect dark galaxies that are very faint or composed primarily of dark matter. It also observes the era of cosmic dawn, when the first stars and galaxies. The array comprises 66 high-precision antennas, 54 of which are 12 meters in diameter, and 12 that are 7 meters in diameter. These antennas, accurate to within a fraction of the thickness of a human hair, can be reconfigured and repositioned, providing varying levels of resolution and sensitivity according to the requirements of different observing projects. The area surrounding ALMA is designated as a radio quiet zone, where radio transmissions are stringently controlled to prevent interference with the sensitive detectors. To further reduce noise and increase sensitivity, the electronics of each ALMA antenna are cooled to incredibly low temperatures. Due to the challenging environmental conditions, most operations are controlled remotely from the Operations Support Facility, OSF, located at a slightly lower altitude of 2,900 meters. The OSF serves as the operational hub, housing offices, laboratories, and antenna control units. The antennas themselves can be relocated using two custom-made transporters, Otto and Lore, for various array configurations. The telescope's complexity and the challenging environment in which it operates make ALMA a very expensive telescope with a total cost reaching approximately $1.4 billion. ALMA operates in two primary modes: interferometric, where signals from multiple antennas are combined, and single dish, where each antenna observes independently. This diversity in operating modes allows ALMA to achieve high-resolution studies with an array of 50 12-meter antennas and wide-field imaging with a compact array of 4 12-meter and 12 7-meter antennas. ALMA possesses 10 different band receivers, each designed to receive a specific range of light wavelengths. The power of ALMA comes from an advanced technique known as interferometry. This technique merges the signals from each antenna to mimic a telescope as expansive as the furthest distance between antennas. This unique feature allows ALMA to achieve resolutions far surpassing those possible with a single antenna. One of the world's most potent supercomputers, the ALMA correlator, is deployed to combine the signals from the antennas in the array, performing up to 17 quadrillion operations per second. Since its inauguration, ALMA has made substantial contributions to the field of astronomy, leading to thousands of scientific papers. All data from ALMA observations are preserved in an archive accessible to scientists worldwide, ensuring the continued growth of its scientific impact. ALMA's exploratory prowess is highlighted by its ability to study magnetic fields in space by observing the polarization of light, and its ability to detect methanol masers, radio emission amplified by molecules, in regions where stars are forming. Thank you for watching.
Okay, so this was like a video for the ALMA. Now I'm going to explain about the ALMA. So here we go. What is ALMA? So as in this video, it was talking about this. ALMA is a large millimeter submillimeter array telescope of 66 antennas, which can work together as a single antenna with a total diameter of 16 km. Although construction of the array it continues until 2021 finish. So this is the. So why we use Chile? The Earth atmosphere and the water vapor is absorb this submillimeter radiation. Facilitate operate as submillimeter wavelength need to be located at high altitude and in dry places. So ALMA and the Chile, that place was the best place, which is quite dry and high altitude. So why is ALMA so powerful? As you can see on the right diagram, because it is located 5,000 meters, around 6,000 feet above the sea level on the Chunju Plateau in the Atacama Desert. The altitude and area make it exceptional site of astronomy. The minimum amount of water vapor at this site provides the transparency needed for the antenna to capture millimetric radio waves without distortion. So here we can see, as I told you, this is due to the quality and quantity of the antenna and square meter, and it has like cover like 66 antennas with the 5,000 altitude. So here we can see why we observe the astronomy. Now we also know that warm, cold, and dark matter exists thanks to the measurements of the wide range of wavelength emitted throughout the universe. Even after centuries of astronomy observation, scientists today know little about the universe. ALMA study of cold matter permit the observation of all planets and galaxies too faint to be detected by optical telescope, allowing us to learn about the early universe. So why we can see it in the universe? Scientists technology developed today allow scientists to design equipment that can capture a wide range of wavelength. Optical telescope on the left side, you can see, which observe the light of the star and hot gases emission. Light right top, and this one is the optical. And then we talk about the ultraviolet and X-ray. This one Observe the study very hot gases and ultra energy. Then we will have a infrared. Observe the study warm and hot dust. Then we have a radio. This one the radio. Capture radio emission from the, and this one will the observe the millimeter and centimeter wavelength. So what ALMA can see? By observing millimetric wavelength, ALMA can see the so-called whole universe where planets and galaxies are formed. ALMA has an unprecedented capability for discovering the presence and distribution of molecules in space and can observe with high resolution masses of cold and warm gases. By observing the invisible, ALMA can see our sun in detail and capture light emitted by particles rather than light reflect them. Thus, ALMA opened on possibility for astronomical research, from the discovery of the new interstellar molecules to the mystery of our cosmic origin. So this is like brief history of the 1933. The American radio engineer Carl Jansky provided was the possible to capture certain band of electromagnetic radiation coming from the universe with antennas similar to those. Later in 1937, Grobner, another American engineer, built the first parabolic radio telescope in order to capture the registered radio wave. In 1938, Ribert was able to detect the radio wave emission from the Milky Way. So how these antennas work? So most antenna used in radio astronomy has a reflective surface that is parabolic in shape. Because of its geometric characterization, a parabolic antenna can efficiently capture signal that reach its surface and direct it to the signal point known as the focal point. So this is like a focal point. The wavelength concentration at the focal point or channel to band receptor located behind the antenna at the so-called front end, and where signals are amplified and digitized so they can be processed. So here we can see telescope capable to capture details dependent on the two things: the diameter of the collection surface, the color of the wavelength of the light. The greater the wavelength to be captured, greater the diameter must be. In order to observe with the sharpness of the human eye, a radio telescope such as ALMA need to be at least 500 times wider than the human eye. The construction of such enormous antenna, however, is impossible. The scientific community has solved this thing using a technique of interferometry. So interferometry is more like an antenna is made up of various panels, and the antenna would still work if one of the panels were missing. It is possible to group together multiple antennas inside a large defined surface area, where each antenna acts as a panel within this virtual antenna. When a group of antennae synchronized observe the same object, and the signal captured by each one are directed simultaneously to a signal focal point, and an image is obtained that is equivalent to a resolution to an image, equal in diameter to group of antenna, and the successive element in located in plateau with a form of interferometry maximum diameter of 16 km. So ALMA versatility. The technique of interferometry invented by the British astronomer Martin Rayl in 1950 not only allow for the greater diameter, but also enable redistribution of the antenna depending on the resolution required for each of these. The more detailed data are needed, the greater the diameter of which the antenna will be distributed for greater resolution. If greater amplitude is needed, the antenna will be grouped together in a smaller diameter group in order to cover large portion of the sky. ALMA has two transporters that can move antenna from diameter requirement for its observation. The transporter known as Otto and Laura were specially designed to move heavy antenna, which is for 54 and 4 minor antenna. So this is how we ALMA transfer wavelength into images. Each antenna has a front end where band receptor convert wavelength into electric signal to be sent to the back end, a complex and accurate electronic system where the signals are digitized and synchronized and then sent via fiber optic to center computer to known as a correlator. This is the correlator where it can do the correlation data processing, and this is the front end. Then we do the interferometry whole antenna, and this is the back end, the focal panel, analog to digital. So this is how we ALMA normally works. So how can we observe through ALMA? So normally each year the scientists compete for observation time by presenting proposals that evaluate for scientific priority with given projects from the countries like finance ALMA North America and 14 European this thing. Those astronomers who propose are admitted don't have to travel ALMA to carry out observations, instead they will remotely ex exclusive access. ALMA has an exclusive software structure that allows astronomers to do many things for generating an astronomical project to receive data from the observation proposal. So this is the like history of ALMA. In 1980, the international scientific community developed an interest in creating radio astronomy. In 1995, the European Organization for Astronomy Research in Southern Hemisphere, the Natural NRO of the United States and the Japanese began to carry out exploratory trials. 4 years later, in 1999, the three observer signal corporate agreement to install ALMA in Chile. Another 6 years passed. The foundation was laid on the plateau and initiated construction of the ALMA observatory. So there are some companies which is making the antennas for ALMA in Netherlands and America. So ALMA is now operating. This means a huge leap forward. The astronomer ALMA will have sensitivity and resolution 100 times greater than the sensitivity that is predecessed. As it happened with the greater telescope that have preceded, ALMA will allow us to see things, the universe, which we weren't able to see. So these are the bands currently the ALMA is working on, band 1, 2 to 10, and we can see it starts from the lowest band, and these are like some are in construction, like band 2 is under construction, but like band 1 to 10, like 35 gigahertz to 1 terahertz is still in working condition to see the universe. So now we're going to talk about the black holes, because our main objective why it is good to use ALMA. So this is the graphical illustration of two types of supernova. Supernova is like type 1, a binary star system and it became a white dwarf when it's getting die, and in the end it became detonation. The second is the type 2 the supernova, which is the huge which has a hydrogen and a helium, normal star fusion, and then it's a massive star imploding, and then we have a core rebound hydration and it will move an explosion. And because it is a bigger star, mostly the bigger star, the type 1 is kind of like for the smaller star, type 2 supernova for the bigger star, and that can make the black hole. So this was like supernova type 1 and type 2. So here we can see the center engine of the active galaxy. This is a black hole. This is the leading theory for the energy source in an active galactic nuclei. A black hole surrounded by the accretion disk. Here we can see the accretion disk. The stronger magnetic field. Here we can see the strong magnetic field in the middle around the black hole. Channel particle into jet propulsion. There you can see there is a jet perpendicular to the magnetic axis. The center and engine of an active galaxy. In any active galaxy, the center black hole may be billions of solar masses. The accretion disk is whole cloud of interstellar gases. They have interstellar gas and dust. They may radiate away as much as 10 to 20% of their masses before it can disappear. So this pair of images show evidence of the black hole at the center of NGC 4261. Here we can see this is the black hole, this is the jet, this is the jet, and this is like a center engine. This is for the M87, the center portion. This is just kind of like a center portion showing rapid motion, and a jet. This is the jet characterized of the material surrounding of the black hole, and this is like intensity of this thing from the here, and this one from here, center edge of the galaxy. And again, one might expect the radiation to be mostly X-ray and gamma ray, but apparently it is often reprocessed in the dense cloud around the black hole and remit at longer wavelength. So particles will emit synchronotic radiation as they spiral along the magnetic field. This radiation is visibly non-stellar. Here we can see these are like the particles, synchronized radiation. and these are the magnetic field. And then we have, like, here's the frequency and intensity, and the synchronized radiation, and the thermal radiation. So particularly emit radiation as they spiral along the magnetic, if they are spiral along the magnetic field. This radiation is decided non-stellar. So here this galaxy is viewed in the radio spectrum mostly from 21 centimeter radiation. Doppler shift of the emission from the core show enormous speed very close to the massive object of the black hole. So here we can talk about the masses of the black hole. The mass of the center black hole is well correlated with the mass of the galactic block. For those galaxies where both have been measured. Here we can see this is the mass of the block, and this is the mass of the black hole. Here you can see M87 is very huge, massive. It has a 10 raised to 12 mass. It has a very huge mass as compared to Milky Way. Is very small. It has a very small mass. And Cygnus A and G black holes, and the M81 is the highest and the biggest mass than the other black holes, and Sagittarius A as well. These visible and X-ray images show the two supermassive black holes orbiting each other at a distance of about 1 kpc. They are expected to merge in about 400 million later, so they will merge in 400 million. So this is like quasi. This is the quasitary we see are very distant, meaning they exist a long time ago. Therefore, they may represent an earlier stage in galaxy development. The quasitary in this image are shown with their host galaxies. Many appear to be involved in collision. The end of the quasitary seems to have been about 10 billion years ago. All the quasitary we have seen are older than. The black hole powering the quasitary do not go away. It is believed that many, if not mostly, galaxies have the supermassive black hole at their center. So this figure shows how galaxies may have evolved from earlier irregular through active galaxies to the normal elliptical and spiral we see today. Here we can see this whole thing, the major merge, and this is the one, the normal spiral. Okay, the mass of the black hole, the mass of the neutron star cannot exceed about 3 solar masses. If a core remnant is more massive than them, nothing will stop to collapse, and it will become a smaller and smaller, denser and denser. Eventually, the gravitational force is so intense that even light cannot escape. The remnant has become a black hole. The radius at which the escape speed from the black hole equal the speed of light is called the Schwarzschild radius. The Earth Schwarzschild radius is about a centimeter. The Sun is about 3 kilometers. Once the black hole has collapsed, this Schwarzenegger radius takes on another meaning. It is an event horizon. Then we call this thing Schwarzenegger is an event horizon. Nothing within the event horizon can escape and the black hole. So now we'll talk about the Einstein theory of relativity, because we're talking about the black hole. Special relativity, the speed of light is the maximum possible speed, and it is always measured to have the same value all observed, as you can see here. So special relativity, there is no absolute frame of reference and no absolute state of rest. Space and time are not independent but are unified as space-time. So this is kind of Einstein theory of relativity journal. It is impossible to tell from within a closed system whether one is in a gravitational field or in acceleration. Here we can have an aviator and we aviator accelerator. So Einstein theory of relativity is a matter can grab space-time, and in going so defined straight line, the path a light beam would take. A black hole occur when the indentation caused by the mass of the hole become infinite deep, as we can see from here. In the late 19th century, Michelson and Morley did an experiment to measure the variation in the speed of light with respect to the direction of the Earth's motion around the Sun. They found no variation. Light always travels at the same speed. This later became the foundation of special relativity. taking the speed of light to be constant lead to the some counter effect, length and constraint, and relativity simultaneously. The gravitational effects of the black hole are unnoticeable outside of the few shots in radii. Black holes do not suck in material and any more than extend mass. So matter encountering a black hole will experience enormous tidal forces that will both heat it enough to radiate and tear it apart. So space travel near him, a probe near the event horizon of a black hole will be seen by observing and experiencing dramatic redshift as it gets closer, so that time appears to be going more and more slowly as it approaches the event horizon. This is called gravitational redshift. It is not due to the motion, but is due to the large gravitational field presence. The probe, however, does not experiment any such shift. Time would appear normal to anyone inside. Here we can see similar a photon. This is a black hole, event horizon telekilometer. A photon escaping from the vicinity of the black hole will use up a lot of energy doing so. It cannot slow down, but its wavelength gets longer and longer. So what inside the black hole? No one knows. Of course, present theory predict that the mass collapse until its radius is zero and its density is infinite, but it's unlikely that this actually happened until we learn more about what happened in such extreme conditions. The interior of the black hole will remain a mystery at the moment. So this is the observation evidence of black hole. Black hole cannot be observed directly as their gravitational field will cause light to bend around them, as we can see from here. We will show you the picture, a video about this thing. And also, this bright star has an unseen companion that is a strong X-ray emit called Cygnus X1, which is thought to be the black hole. And this existence of the black hole binary partner for ordinary star can be inferred by the effect of the hole have on the star orbit or by radiation from infalling matter. So here we can see Cygnus X1, the X-ray is a very strong black hole candidate. Its visible partner is about 25 solar masses. The system total mass is about 35 solar masses. So the X-ray source must be about 10 solar masses. Hot gas appear to be following from the visible star to an unseen companion. Short time scale variant indicate that the source must be very small. So there are several other black hole candidates as well, with characterized similar to those Cygnus 1. The center of many galaxies contains supermassive black hole about 1 million solar mass, as we can see from here. This is the black hole and this is the jet. Recent evidence for intermediate masses black hole has been found. These are about 100 to 100,000 solar masses. Their origin is not well understood at the moment. So this is like test for the general relativity. If this is the sun, deflection of the starlight by the sun gravity, because of the sun gravity, by during solar split 1919, the result agreed with the prediction of the general relativity. If this is the actual position, and we can see here the image, apparent position of the star, and this is like to prove of the general relativity. So test of the general relativity, another prediction. The orbit of Mercury suppresses due to general relativity effect near the sun. Again, the measurement agreed with the prediction, as we can see from here. New window, the gravitational wave have opened a new window in the universe. The general relativity predict that the orbiting object should lose energy by emitting gravitational radiation. The amount of energy is tiny and these waves are very difficult to detect. A neutron star binary system has been observed, 2 neutron stars. The orbit of the star are slowing at just the rate of predicting if the gravitational wave carrying off the lost energy. So recently, the physics showed the LIGO, the laser interferometric gravitational wave observation designed to detect gravitational wave. It has been operating since 2003. So a new window in the September 2020, LIGO first observed gravitational wave from the merger of two black holes. When two black holes combine together, and then we did the LIGO first observed the gravitational wave to prove there is a gravitational wave. Do black holes exist? Evidence has been mounted, but no direct observation of the event horizon or the first-hand measurement of the black hole property has yet been made. So probably, but not definitely yet. So this is the formula, general theory of relativity. Here, this left side is geometric of the space and time, and on the right side is the density of matter and science. John Wheeler says space-time tells matter how to move, and matter tells space-time how to curve. He provides the exact solution of the general theory of relativity. So this is the video where you can see what is general theory of relativity. So now this is the two black holes. One is the 187, which is taken by the ALMA, and the right is Sagittarius A. The black hole imaging at event horizon scale, and it has a magnetic field near the event horizon. There is some magnetic, and you can study this accreditation disk gravitational physics about the gravity of the. So ALMA, what is doing right now is reading about the gravitational field and the accreditation disk using the interferometry techniques. So this is like a black hole video. We just talk about some black hole. This is M87 black hole. How they take the image. And this is how the technique they use in the interferometry technique, using different antennas at different position from south to north, and then taking the signals, constructive and destructive, to see the image of the black hole. So this is the gravitational theory of the Einstein. This is kind of like a black hole. How the light comes and it diverges. This is the general theory of relativity, as we can see from here.
This
So we now talk about this was where I was showing you the event horizon, the global VLB, very large array, very long baseline interferometry array of antennas, and combine them together to see the two black hole, the Sagittarius A, which has a mass of 4 into 10⁻⁶, and M87, which is the higher mass, 2.46 into 10⁹ and width have is some size micro 40 micro arc second. The size of the Sagittarius is 40 micro, but the M87 is much smaller than Sagittarius. It is 21 to 30 micro arc seconds, the size of the black hole. So this is the technique they use, and this is the ALMA here in the middle, and they combine them together. This is the image. They take the from the north and from the south, and they make 2 points here, and slowly as the antenna moves, and they point it out in this graph, and then they make the image of this thing. So this is like black hole 87 breaking the model. Here we can see the jet propulsion, jet structure, and they use it breaking the generation, how we take the imaging. So here is like taking the averaging of image of the black star, how we take so many images as we talked about before, and then we combine them together and make the image. Here is the video. So this is like a kind of like an imaging approach for black hole. Like we take this all continuous image, and then we will do the image approach, do the averaging. Average clustering image, cluster 1, cluster 2, cluster 4. And eventually we choose the best one, which is it is like this average one is the best one. We choose this image, like we do to Sagittarius A and the black M87. So here is one example for the black hole now. Here we make a clustering, and we image approach the same technique like we did before. I will show you before. So then we divide it into 4. We have so many peta data images, and then we combine them together. Like this is the Sagittarius A image of the black hole, but normally we do like we make it into 4, divide into 4. As you can see here, it's selecting here. Then we make 1, 2, 3, 4, and then we can choose which best suit. Like we have 1, 2, 3 here, and this is 1, 2, 3. Here is only 2, and then this is the best image for the Sagittarius A. This is how we do the clustering, and after we do the interferometry from different antennas, and then we combine them together and do the coloration and the clustering image, and then in the end we get this thing. So this is like with one I was showing you before, that this is like the neat result of the Sagittarius image by using the which have the size of 50 micro arc second. So this is the technique of interferometry polarization, because the light the accretion disk we see is so much huge high that you cannot see the things very clearly. So we use the same technique of the polarization. As you can see, there's a 2 antenna. If we have a single mode, then we use x-axis. If we have a dual mode, then we use x-axis and y-y. I'd like to do this with the stroke 1, the stroke equation. If we want to use full polarization, the full coloration, we will have a full colorization xx, xy, xy, y1, and this is how we can use the polarization technique to see the image very clearly. If we don't use this technique, we cannot see things very clearly. So this is one example. This is interferometry polarization observation I, Q, U, V, where we can see the V is for the circle polarization, and I It is the total intensity stroke 1, and this one U is for the linear polarization, and this one is the EVPA is for the tangent Q for the Q. This is like for the polarization formulas for the circle. There we have circular or linear polarization. I don't going to explain this in too detail because this lecture is for black holes. So this is like then when we will have a jet structure and jet launching structure of the black hole. Thank you very much. Thank you very much.